Good morning. I didn't hear anybody. How about good morning? Well, thank you. I need to be woken up, not you. So, the deal is, we're going to make a presentation today that I hope everybody leaves a little excited. More importantly, we want to give you some direction, some steering currents to a different thought process of how we do engines. Before I get into this, though, and starting this, I want to introduce Dan Begle. This is the guy, he's forgotten more than I know, so he's fun to hang around with, but I'd like for him to give you a history on him. Dan?
Thanks, Randy. So, my name is Dan Begle. I'm the technical sales engineer for MAHLE Cleveite engine bearings. Sorry about that. My background prior to MAHLE is I was 27 years in NASCAR racing in the engine shops. The last 13 years I was at Roush Yates, and the last 9 of those I was the reliability engineer. So my job was to look at parts, evaluate wear, evaluate testing, validating new parts. So come to MAHLE, I work with a lot of performance engine shops. I work with production engine rebuilders, looking at solutions to problems that are facing out in the field. And as things come up, we're also fortunate to have their test lab where we actually did a lot of the testing on the OE cars before they came out. So it's interesting, the guys in the test lab, it's the stuff that they saw 20 years ago developing the engines now is coming to the aftermarket into newer vehicles, and we're seeing what the end result is after their engines are worn out. So tying all those together, coming to the aftermarket and bringing new ideas, concepts, and thoughts. So we had this idea about a year ago, working with our Germany, Randy and his balancing, of coming together and discussing crankshafts and what's happened. Because at the end of the day, we can talk about bearings, Randy can talk about cranks, but the reality is, when you bolt it together, it's a system. So we were talking about the system of the crankshaft bearings and what you're seeing with the bearings, the effects of crank balancing, crank design. So we'll move forward here.
Okay. Now, of course, talent, humor. All right, so that's how this is going to go. All right, so at any rate, my history very quickly is, and the only thing I can claim any fame to is that I'm the husband of Judy Neal. So I have been blessed with being in this industry for just about 50 years. And I started, like a lot of you, at ground zero. You guys talk about cleaning equipment. Now our cleaning equipment was some sort of a siphon hose with mineral spirits, and off we went with a brush. A lot of things have changed, and that's what we're going to talk about today. What we thought we knew, we really don't know. And if you'll open your thought process to what has changed, and something like I say, we're going to give you a couple things here that we hope will add a lot of benefit to how you build your engines, and more importantly, make money building your engines. So let's cut right to the chase here. I'm going to give you an outline here of what our topics will be. So we're going to start with evolution of engines. We're going to move into bearing function, followed by torsional harmonics, and then balancing dynamics. That's a mouthful. Now, normally I could take about a day and a half to even touch this lightly. We're going to do it in just under, well, a little over an hour. All right, so here we go. First thing we want to understand is how the industry has changed. Now, on the left side of your screen there, you see back in the early Corvettes, 265 horsepower, cubic inch, 195 horsepower. Basically, peak RPM about 5,000 RPM. That was a go-getter in its time frame. Now, we're building 500 cubic inch engines. Now, these are still normally aspirated, right? We'll talk about you boosted guys in a minute. But this guy is sitting there at 10,000 RPM, doubling that up, and they're 1,500 horsepower plus. Very impressive. This is the evolution of how we've gone over a couple decades. All right, then we have this bad boy. Now, this is the one that's fun to watch because 500 cubic inch, 11,000 horsepower plus, depending upon whose tuner you want to talk to. And so here's what's cool about that, though. Very entertaining. All right.
I notice there's a couple of these fuel guys here. They can relate to this, right?
By the way, I'm one of those guys in the early days that used to have a front engine car. That was no fun. The guys where you're sitting now, you're sort of blessed a little bit. All right, so here we go. We're back to this, and this is where our world really lives. In other words, we have to understand technology is the only mechanism that we have to push forward. Now, a lot of what we do and what we'll be talking about here is, I'm going to say, good ideas, ego-driven. I think we can agree with that. But the deal is we want to try and clarify how you need to move to the next level. All right, so what we're going to do is we're just going to go some basics here. Keep engines simple. Pistons go up and down, cranks go round and round, but you see the other mechanisms that's all entrenched into the function of the engine. In other words, I used to say the knee bone connected to the shin bone, blah, 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 blah. Everything there has its unique function. The problem that we have is it also has a problem within itself. And so we have to start understanding what that problem is. One of the things in the old days, we used to just use a standard timing chain. We still do. Belt drives seem to be one of the evolutions there, and it did and has merit to dampen some of the harmonics created by the crankshaft. Gear drives, you know, and I can go back to the original Jackson type, man, those things not only were they noisy, they were first generation stuff. They've evolved, and it's getting better. Gear mesh, by the way, is a critical part of one of the improvements. Now, what I'm really trying to link here is understanding of how frequencies affect materials. Virtually everything out there has a critical frequency. Now, I borrowed this thing, I pirated it actually from Haas, but what we have here is two tuning forks, and you can see a little ping pong ball. There's actually a little hair wire there, but they are isolated. Now, the isolation is he's going to strike it, and it's respond with non-contact. Now, there is contact action, it's called air. But remember, we probably, other than gap of the valve lash, everything else really runs in direct contact, so it's easily transferred. Now, what he's going to do here is he's just going to change frequency. He'll strike it, and notice the response, nada. All he did was change frequency. Now, every single thing in your engine, from casting to forgings to rolled steel, everything that's there has a frequency. And you got to appreciate everything you put together in perfect world is in harmony. Nice try. Chaos is a better word. All right. So application of engine bearings and the operating environment. So what I'm going to do here is I'm going to turn this over to Dan for a second here.
So before I get started, I want everybody to understand, we all put in bearings. We understand that I put in thousands of bearings, and I never understood a bearing like I do now, working with MAHLE and how they function. I design bearings and the effects that they have. So just kind of go. We have the crankshaft here, and bearings have a wedge. So there's we call it eccentricity. So the bearing has basically, with the force coming down, as we would think, down as if this being firing pressure on the top, you have a wedge space here, and as the shaft is rotating, it is pulling oil into to self-lubricate. Notice it's self-generating. So you'll hear me mention sometimes film pressure and film thickness. I'm not talking oil pressure, because oil pressure comes in from the top, side, somewhere up in this area. And as this comes in, it's basically like a door wedge. If you take a door wedge and you kick it in underneath the door, what's it trying to do? It's closing the door, lifting up on the door. It's putting pressure up. Same thing happens on an engine bearing rod or main, that as it's turning, it's taking a larger amount of volume and putting it into a smaller space. So you're going to hear me mention film pressure. That's technically right here. So now, as we know, the engine fires, pressure goes down, right, trying to push the crank out the bottom. But that's not always the case. The pressure doesn't, as you're going to see, the pressure doesn't always go down. It's moving around, and that's part of the big thing of what we're seeing on engine bearing wears and what we're going to address. So typically, a connecting rod bearing, the load will go oval. All right, so typically a rod bearing will have ovalization of the housing board, and it depends on the rod itself. All right, so there's bore relief on the edge of the bearing to compensate for this pressure load that will want to pull the bearing in. There's also bore relief on the main bearings, because there is movement based off of what cap, what block, what's going on with the bearing itself. But a connecting rod, the force is not round. So the interesting thing is that's 720 degrees. The oil pressure, as you can see, this is 720 degrees of rotation. When the piston If you think about on the exhaust side, the piston is trying to escape through the exhaust port. It just wants out. There's nothing stopping it other than back pressure through the exhaust. So it's actually lifting off of the rod journal itself, and you actually create a negative pressure right here in rotation of that crankshaft because it's pulling away. Remember the film pressure? All right, you're pulling away, so at that point, you've created a void. Your pressure fell down. As the rotation goes in, typically speaking, right there in rotation is going to be where the bearing's going to contact because you ran out of oil right here. All right, so we're going to keep all this in mind. So I'm trying to explain just the functionality so it makes more sense to you as we go down the road here. So this is a typical FEA model of a single cylinder crank. 2 journals, main bearing 1, main bearing 2, and a rod journal. So the simple thing here is typically when the FEA, we've added a force load of pressure, and you can see there's tilt going on in the main bearings. All right, in this case, we have 41 microns on the number 1 main bearing, 27 microns on number 2. Now this can be exacerbated by mass weight that's on the front or mass weights on back, but which one's going to do. But a lot is the crank itself and just pure flex on the crank. All right, now this is a single cylinder. So in this particular, the same application, same crankshaft, we actually did, and again, here we're going to go back to peak oil film pressure. That's what I was talking about the oil coming in. So as this is rotating around, this is the FEA analysis of showing where it was at lowest peak oil film pressure. Actually, the bearing is right there, and you can see the alignment of where it's in danger, red being danger, to right afterwards, correct? Right afterwards is where it's showing losing part of the bearing because of low oil film pressure. Now the interesting thing about this test, single cylinder engine, and we used a single cylinder simply because that was what the customer was working on. This was an actual customer. This was not simulation. This was a testing that we did in Germany. Most of this data I get is from our home company in Germany, which we make a lot of OEM, so we established testing for that to help that customer out. The interesting thing about this is 6,500, it was in danger. At 7,500, it got better. Now that's puzzling. Me and Randy have kicked this around over and over. It's like, how in the world does it get better? And there's some things when you're going to leave here, the answer is, don't really have an answer because there's a lot of stuff going on, and that's kind of what we're talking about. But you can see danger in how this is happening.
Actually, there's a couple of relationships there. We know flexure is involved, right? As we generate pressure against any object, it has to either support or surrender. But the other side of it is, as we've changed the RPM, we're also changing frequency relationships. So the materials themselves have a different characteristic. So as we're diving into this, I'm going to turn it back over to Dan in a second. You got to understand, we have to open our ears and our minds a little bit to understanding this is not a 7,000 application. It's 7,500, it's 8,000, it's 10,000, it's 18,000 if you're Formula One. And so this thing changes the profile during its entire span. All right, want to switch over to another one?
Yep.
All right.
All right, so here we're talking about, now I was talking about film pressure. So the film pressure was, again, the oil squeezing down, creating high pressure. So when if you take a volume of oil and you squeeze it real hard, it's going to dissipate. So now we talk about oil film thickness, all right, which was actually there keeping the journal and the bearing separate. So as you can see, same RPMs, a lot of danger because it squeezed the film pressure so much we have a void in oil. Again, the harmonics changed, 7,500, it's actually running better. This was, I know a lot of people, big engines, a lot of horsepower, start-stop technology, we're seeing more and more people on the typical start-stop engines, adding power, things going on. The interesting thing, I did some looking at start-stop minimum oil film thickness on main bearing 1. So at 200 RPMs, there's some serious problems. So I don't know about you guys, but I travel a lot, rental cars, and as soon as the green light hits, man, you nail the throttle and going, right? So this is what happens every time to that bearing, main bearing 1, is it's in danger every time that engine starts. So there's some production engine rebuilders in here, thinking about this as you're doing the engines, what's happening. 400 RPMs, it's starting to get better. So every time that engine starts, you're putting contact on that bearing. This
Does it repeat itself again higher up?
No, because at that point you're self-generating and you're creating an oil film pressure in there, and it will come back to normal operating condition. Yeah. Yeah, the question was, will that continue as the engine runs? No. Once it gets running and oil pressure gets in there and it's straightening itself out, because a lot of main bearing 1, a lot of it is getting motion of camshaft, whatever's on the front, of getting the moment of inertia going is causing the flex. So great question. Start-stop rear main oil pressure. All right, now we step on the gas, take off. You saw what happened to the front. This is the rear. The reality is, in several engines that were tested, there is no oil pressure in the main galley until 3 to 3.5 seconds, and then it speeds at 600 RPMs in less than 1 second. So as oil pressure is green, your oil pressure is coming up, your engine RPM is already up here, and there's 0 oil to the rear main. Frightful. So go with.
One of the things you want to say, well, who cares? I rent cars, it blows up, we turn it in, right? Well, no worries. Me and Hertz don't get along very well. The deal I'm trying to get to here is that there's a correlation here to when we have a lot of guys building really nice, high-powered engines, don't realize that that trailer trip across the country wasn't pre-oiling anything. In other words, an aircraft, if you let an aircraft sit long enough, you're going to find that it's going to sit there and wipe out the camshafts because nature takes its place, gravity pulls away. Dry starts, the only thing I know about this guy, if there's no oil, that's the worst thing you can have. I don't even care what the grade. You can say, well, the additives. But the bottom line is there's a correlation here to high performance.
Absolutely.
Okay?
So this was the same engine, same testing, the oil and film test. This is MAHLE's Sabre. It's a data acquisition to give us the data we want. So to understand that, AVL was the actual dyno it was tested on. Very accurate, very nice dyno. On the rear main bearing. So at startup, 300 RPMs, again, you see an issue with the pressure. The AVL showed the exact same issue. There's the actual bearing itself. So we saw a good agreement, but this is the rear, all right? Same thing happening, all right? What's on the rear of the engine? The flywheel, something, converter, whatever, mass weight. All right, so now you're running it and you're starting that engine up. The oil film is minimal, because we just talked about that, right? There's no oil back there. Now you've already worn through the overlay and you're into the substrate on the rear. Notice how this is on the rear and not all across the bearing itself, because there's that much deformation in the crank that it's flexing around. There's that much bend in the shaft itself. So
I'll run down a minute.
oh, sorry.
As you're moving away from that number 1 bearing stuff, has any of your modeling been done with belt load and crankshaft snout length as variables on that modeling?
No, nothing that I have for that, because the way our data works is we are given the engine and how it's designed, and then we're making parts for that. So that is determined and it's given to us as far as snout length and so forth like that. So that to us, that's a given fixture that we have to work with.
Because as a past employer, we had issues with number 1 bearing in a
All right, hold on one second. Chris? Yes. I'm nominating you as the official mic handler, all right? You didn't know you were going to do that today, did you? Well, thank you for volunteering. So if you'd be so kind as to hold that mic, and anytime we have a question, this young man is going to save the world, because this is all being recorded, and so we hear the question, but the recording doesn't. Now, there's a bonus at the end, I promise you. I'll like it, you won't.
Wow.
If you don't mind, as we go through this stuff.
We talked about this earlier, Randy.
Yeah,
Okay, so remanufacturing, to me this was phenomenal. Okay, we talked about oil film pressure, oil film thickness. Okay, now keep that all in mind here. So measured crankshaft lobing, this was grinding the crankshaft, all right, or wear, however you want to look at it. So this is the red being the profile of a perfectly round, because at the end of the day, when we design parts for MAHLE, we consider the housing bore round, everything, the journal is round, but the reality is as it runs, we know it's not round, and after it runs, it's even less unround. So that's not really a word, but it makes sense. So in this case, we have, let's say the new engine's coming in, thinner oil, or you're building race engines and you want tightening clearance up, thin oil. Coming from NASCAR, we ran some super, super thin oil. So clearance just got really tight. Keep everything in mind here, what we're saying, tight. You have to really work to know what your oil is doing. Oil management is huge. Crankshaft surface finish. We're going to touch on that a little bit. So in this case, we have a crank pin, number 2, 3.43 microns of, you can see it's not perfectly round, from grinding chatter. All right, crank 4, 2.83 microns. All right, so think about that squeeze effect going on again. What's happening with the perfectly round circle versus this with chatter, right? It's pumping. Right? Here's the FEA. You can see the 3.43. It's a lot of red. 2.83, not quite as much, some danger. That little bit of difference, again, on this simulation, on this engine application, we have found that number 2 put the peak oil film pressure at 159 megapascals versus 136. That put it in the position that it had bearing damage to the point of you're in failure mode by grinding chatter on the shaft itself because of the pumping action that it's doing. Go one step further, maybe. So, there we are. Okay, so we're going to polish the shaft. All right, shaft is perfectly round. We polish it. And I'm not going to get into the polishing aspect, but polisher can be your best friend or your worst enemy, all right? As you're polishing, the hand polishers, you get some bounce going on that thing. You get oil holes, and it's changing the polishing around. And in this case, it's, do I have that? I don't have that. How many microns it is? 40 to 60, so I'll have to figure that out, it doesn't matter. But in this particular case, polishing, and this was actually a real engine. This is a customer, a manufacturer customer sent this to us. So this is not something that just made up. This is real life happened, and it's a major manufacturer, where they were having lobing from polishing the crankshaft. So it created that lobe. Again, there's the line, oil film pressure, we talked about that right there. Again, right after it, there's your piece of your bearing missing because it created a problem where you lost oil right after as the rotation of the engine goes, simply from polishing the crankshaft.
We're going to hit on this at the end a little bit, only because of all the things that we witness in the field, is that we find, for the most part, old processes are, because of naivety, and that's why we're trying to enhance here with this discussion. You can take one of the best cranks made from the best manufacturer in the world and screw it up. And you got to be very careful where you're going with that. So it's a change of process. You've got 2 choices. Do what you've always done and pay the penalty, or learn how to restructure the process and get benefit. It's literally that simple.
Yeah, somebody told me one time, you know, there's the old saying, practice makes perfect. Now it makes permanent. Our thoughts are what was permanent to help you think differently of maybe it's not the right concept of what we need to do. Because just because that's the way it was doing it, things are changing. Performance changes everything. New castings change everything. Again, peak oil film pressure, not going to elaborate too much, kind of same simulation you saw. Again, when the peak oil film pressure went up, as you can see, 216 megapascals versus 169 failure mode. The data supports the actual component itself. So this is another FEA. This is a standard V8 crank. Obviously, you can see all the main bearings, rod journals, typical V8 crank. And what we did is we did simulation on the front journal. It's animated, and it's not animated to exact. You'll see a lot more motion than it really is happening, but it's to exaggerate so you can see what is happening. So the crankshaft's there. Again, red is danger. Down the blue is fine. Things are going well. Firing pressures, adding different stresses, frequencies going into this. So there's the animation. Pay particular attention to the front right up here. Again, over-exaggerated in animation as far as movement, but you can see the flex happening as the engine is in operation and the engine is firing. So the engine's moving. A crankshaft is a spring, right? No matter how rigid you think this piece is, there's some great crank manufacturers represented here. You know, I'm not a crank designer. I never claimed to be a crank designer, and I will go to a point, and that's all I'm going to say. And any crank designs, I advise you go them. But a crank is a spring, and it has to absorb the torsions that are coming in, the pressure loads as the engine's firing. So it will go forward, it will come back, it will go forward. You know, based off firing order, crank design, counterweights, which Randy's going to get into a lot here and later. But in this particular case, if you look right up here in front, you'll see this is a snapshot of that going. All right, so the engine's firing right here. You can see the color of it. You can see the flex going on, and the crank is basically just doing this. As it's firing, it's coming apart and spreading. All right, so we can get, again, crank design about offset of cranks and pin size and so forth. That's not the purpose of this. But the interesting thing as I was watching this FEA and the animation is down here. I never thought this counterweight would be excited that much. See all the red? Because of that firing pressure there. That was a whole new concept for me. So when we started thinking about that, and that piggybacks exactly what we're saying. So as this is happening, we talk about journal orbiting. The first time I saw this, it kind of, again, it took me a while to process all this. I'm a little slow sometimes, so it's just the way I work. But the crank is rotating, again, 720 degrees. Firing pressure, typically you want the load going down, right? Because it's trying to push the crankshaft out of the oil pan. That's what we think in our mind. And that is typically correct. All right. So as that crank's going around there, you actually want this crank to be moving around as it's doing here, because you're getting spaces here where, again, remember the eccentricity of the bearing, you're getting oil in, self-generating, the oil's coming in, creating a film pressure, film thickness, perfect world. All right, right here's your minimum oil film, and here. So you're getting two locations here where those are and that's not scary. It's right at where it needs to be and to be expected. The animation we showed before with the crank flexing, now you get what we call crank journal orbiting. And what's happening is same concept, but it's orbiting. So what you set the clearance to, now it's flex and it's orbiting. Randy's going to go in a lot more in this later. But as you can see, now all of a sudden, you ever take bearings out and it's like, why is it worn up here? Because we all know the crank's trying to come out the bottom. This is why, because the crank's orbiting. And you've created a minimum oil film right here. you can see how much difference it is from here to here, and how much longer, right here, you are not getting oil. That's what happens when the crank flexes and why you're getting bearing wear right there. So bearing components, I'm not going to dwell on this a lot. I'm in booth 1601. If feel free to stop by afterwards. We can get way into this, probably more than you want to, some of you guys, but it's I kind of dig it. Tri-metal bearing, typical tri-metal bearing is a steel backing. It has a substrate and a plating overlay. All right, in this particular, our performance bearings, I'm not going to turn it into a sales pitch. This is a technical presentation, but the sales pitch part of it is this part right here is cleveite bearings are the only bearings that are cast. A cast is this component right here, the substrate. All right,
There we go.
so we'll get into that here real quick. A typical bearing, again, overlay, copper tin lead, substrate, a nickel layer to keep them from migrating. So the thing is, and I say this over and over and over, a bearing is only as good as its lowest melting point. So in this case, you have tin that melts at 360 degrees. So in 360 degrees, if you get frictional temperature above 360 degrees, remember the slide I just showed with the journal contacting, you're getting frictional temperature, not oil temperature, frictional temperature. All right, you don't have enough oil moving through the bearing, you're getting frictional temperature. When you exceed 360 degrees, you are starting to sweat out the tin of the plating. You are in first stage of engine failure. The Q1, a lot of the higher end performance, all the nitro cars, Pro Mods, tractor pull, we run a V bearing, which is a lead indium. The purpose of an indium is allows more movement. As the crankshaft flex, things happen. Indium is an element that will allow movement. It will deform and come back to shape. An H bearing is a great bearing, that a copper tin lead, where it is a harder bearing and it will last longer. It will give you more service life, but is not as malleable that it would conform to torsion twist. So there is a right bearing. Again, not going to get into a whole lot of that right now, but again, feel free to talk about that. We can talk about that at the booth. Coated bearings, a lot of people ask about coated bearings. Coated bearings it's above the overlay because you still want the movement, and it puts a thermal barrier between. Remember, I was just talking about the lowest melting point. You are putting a thermal barrier. That's the beauty of coated bearings. You're putting a thermal barrier to prevent that from getting frictional temperature to melt that component out, the lowest melting point. On the same token, it is a MAHLE based, and it is a dry film lubricant, so that helps when it runs out conditions to reduce that frictional temperature and put the thermal barrier in. So the lot of question is, do I need a coated bearing or not? At the end of the day, it's helping put reliability into the engine. All right, not going to get too much, just so everybody understands, a bimetal bearing is a steel backing. It is an aluminum, 2 layers of aluminum with a core in between, and not designed to hold the pressures of a performance application, but there is a place and a value for that, and it's a great bearing. But this is the part I want to talk about, the casting process. So as I mentioned, substrate, you want strength. There's a cast bearing and a cinder bearing. Cleveite owns the process of casting. It's made in McConnellsville, Ohio. All our performance bearings are made in Atlantic, Iowa. And the casting process is taking copper, tin, lead, and when you take elements of copper and tin and you melt them together, copper, tin, lead, 3 elements, when you melt them together, you create an alloy. The alloy of copper, tin melted together is bronze. All right? If you do not melt them together, copper, tin, lead, and you sinter, which is basically taking the same components and put them in a paint shaker and laying them on the steel backing, at that point, and then you squeeze and heat it, you still have 3 elements. The beauty of cast is, if you look, there's green structures. The black is the lead, and if you look, the black here is the lead here. This is just a sample size, and I'm gonna pick on this guy right there. All right, so if you have a center bearing, that's a soft spot in the bearing. So that bearing is gonna be more spongy. It has no structural support. You can see grain structure, because when you make an alloy, you create grain, all right? No grain whatsoever. That's why sometimes you can actually get crack propagations through here, and it will lose a piece, lack of adhesion. There's a lot of things that happen for that. Same three elements, same percentages of three elements. Cast substrate, you can see the grain. You can see a better bonding. Where centered, and our P bearings are centered. Typically, there's a few that are cast, but a P bearing is typically a centered bearing. It's easier, it's cheaper to make because you don't have the melting process. But again, as you can see, you have not created an alloy, you've created three ingredients that are just heated and compressed together. So typically a cast copper tri-metal bearing, low carrying capacity is around 12,000 PSI, centered is 10,000 PSI. So a lot of people ask, well, what bearing's right? What's bearings right for the crankshaft flex going on there? I'm just a huge cast fan because of I look at it this way, if you're building a house, you want structural support for the roof being the overlay. You want to build out 2x2s or you want to build out 2x6s. All right, 2x2s, you put drywall on there, brick the outside, it looks great. Was it really structurally supported? Just like when you get a bearing, you look at it, it looks great, but you can't see what's between those two walls supporting that roof. All right, so that's.
Why don't we make all bearings tri-metal?
Hold on a second.
Hey.
You gotta flip the switch there if you don't mind. At the bottom.
Okay, can you hear me?
A little louder. Not yet.
Okay, can you hear me now?
Nope. You gotta flip on. This is always the fun part here.
Hear me now?
Let's see. Let me get a tech who.
Okay.
There you are.
Go.
There it
You're
is.
in.
Why don't we make all bearings tri-metal then?
Tri-metal cast or tri-metal centered, so there's both.
Tri-metal cast. If it holds
Because there is an expense difference. It costs more to make a cast because of the amount of process. It's a foundry versus just dumping components on a strip and heating and sintering and squeezing it.
well, industry-wide, is the OE using more centered?
Absolutely.
Because of cost?
Absolutely, because on OE World we bid contracts, and I'm not on the OE side, but I can speak. We bid against other vendors on bearings, and it comes to they're making millions of these, and price is to drive that car price.
Thank you.
Sure, thank you.
Let me build on that a minute, because one of the things about racing, I always have a lot of fun with the fact, your mission is to make power, right? That's what everybody's here for. And then you have an option of selecting materials. And as you increase the load, then the only way to improve this is either through material improvement or in product design. Well, a lot of times your purchase products, and Dan hit it right on the key. People sometimes adjust their belief by way of cost. You guys are on the other end of this scale, not OEM. They got this thing figured out. What you guys need to understand, the key factor to me is why in the world would I put something lower capable into any of the engines? Now, the differential in price per job, tell me what a warranty cost you. Tell me what a failure cost you. And then you're going to talk about pennies on a dollar for a bearing? There's something wrong with that logic. All right, let me move on to it. Whoops.
Other way.
We went the wrong way. There we go. There we go. Good. This one's fun.
So this was just something I put together as we talked about the lead and crack propagation. So if you watch this being the substrate, you can see the crack starts propagating through the lead on a centered bearing. After the shaft is repeatedly bouncing around and moving it, you will get crack propagations through the lead on a centered bearing to the point when the cracks connect, pop, a piece jumps out. So if you ever take an engine apart and all of a sudden there's a chunk of a bearing missing, that's what happened right there. Now, based off of it can go all the ways down to the steel, it can go somewhere into the substrate, but usually that's a centered bearing, and the lead has, because of flex, or just when it's centered, you can have cracks in the bearing itself. So to go to the question of why don't we do that, this will happen. And sintering, it's just part of the sintering process, are the negatives of the sintering process. So this is a animation to kind of show you, kind of summarize all this about bearing flex, what's happening, that I did. I had one of these pipe dreams one night, woke up middle of the night, and this came to me. So I had my kids make me some Jello. And so we're going to use this as a representation, the bowl being the shell, orange being the substrate, and I plated it with a can of Rust-Oleum paint. All right, so that's your bearing as you get it. Everything looks good until the crank starts flexing around and the Jello shakes, your substrate. Once the substrate starts shaking, what happens? You get this fatiguing going on because, again, remember, you're going to build a house 2x2 walls or 2x6 walls. What you can't see is what's hidden between the two layers on a tri-metal, what's in the sandwich. The meat in the sandwich is that substrate right there to support this overlay. Right, so if you ever see a bearing comes out and you get these cracking fatigue marks, typically speaking, there's something happening and your Jello shook. So again, just reiteration, firing pressure and what's happening right here, crank flex. All right, this is all kind of tying in together.
Okay. All right, so let me pick up on this just a little bit because we're going to bounce back and forth here. Key points that we're starting to acknowledge is that the crank is hostile. We're finding that what we think is doing is not what it's really doing. We highlighted this by way of the FEA, so we wouldn't even look at a counterweight before, other than to use it for balance processes. Excuse me. The bottom line is that it now becomes an exciter. There's a key word for you. And it's outside of the sequence of multiple orders of vibration, and we'll talk into that in just a second. But what we're going to do is show you that that flexure causes displacement. So I talked about materials and processes. So actually what Dan's got here is a little bit of a remedy on how we have excessive flexure with conventional bearings.
So what we're working on here is increasing crankshaft requirements. So as you saw the crankshaft's flexing, so if you gusset it via the radius, size of radius, and this is showing a bearing, and at this point, if you increase the radius, what happens where if you get an aftermarket crankshaft, they increase the radius. This is kind of a caution here, what you look at. Increasing radius, next thing you know is you can see right here and there the contact that's happening at the point load of the bearing. All right, so you're now at this point, obviously your bearing's having some issues. You're creating some frictional temperature in there. As the shaft moves lefty right, back and forth for thrust, you're creating some wear, you're creating some friction, you're creating some trauma to the bearing. In certain applications, we've made bearings for increasing radiuses. There's some more on the horizon we work on, or a narrowed bearing, to make sure that your radius, the corners, are not into the contact. So this is a great concept, and I love it, about adding strength. As you saw in the animation, the crankshaft, the flex is from the rod going out. So if you can gusset that, again, with the radius, you're building strength into that shaft to change how much you're springing that crankshaft.
Some of the aftermarket cranks in the manufacturer, by the way, I want to thank Nick Norris for
Yes,
supplying that.
thank you, Nick. I think he's out here somewhere. I saw him come in.
Checks in the mail, by the way.
There he is.
The deal is...
Callie's crankshaft. Huh?
The deal here is that sometimes you're getting a crankshaft by different suppliers that have different radiuses, and your supplied bearings, you just normally put them together, you spun them into the assembly, you think it's okay. Then as soon as you start the engine and you start getting witness areas of contact. Well, two things I'm going to say there. Once that takes place, it doesn't have a messiah to fix it. You're done. And anytime that you start forming material, it doesn't just say okay. It's going to generally generate a byproduct. It's going to cause additional errors. In other words, you're down on a downhill slope. So your assembly processes have now got to change. For instance, even on this particular character, let's talk about end play. If your end play is, let's say 3 to 5 thousandths, if that's the zone you want to put at, but then you happen to take another application, put it in as 15. Well, what you're going to find is you're going to get in that contact area, And you're not, you know, again, before we didn't worry too much about it because our radiuses, in fact, the manufacturers now have learned this is a process change that gives an increase in structural support. So at some point though, the bearing area, contact, where we consider the load, is being maybe compromised. There's a sweet spot. In other words, we can't just narrow this whole thing. But you gotta start taking another look in what we call reading the bearing. Find out what's going on. If it's making a witness mark, that's not a natural phenomenon. All right, that's a cause and effect dynamic. Fair enough?
Correct.
All right.
So again, this is kind of same animation on a thrust. Again, point load. So you know these are areas as you see this. LS came in with some bigger radius crankshafts. We actually made another main set for the LS. 2199 was the standard. 2411 simply changing the chamfer and where clearance was to allow for that larger radius crankshaft.
Yeah, pinch point contact is a no-no, period. But the assembler, where's our mic? At the bottom,
At the bottom,
on the side.
on the side.
We're gonna put a red flag on that sucker next time.
Show it to me, I'm not that smart right here.
See that little sign there?
No, don't see the little sign there.
Talk into this, see it's on.
Hello.
There you go.
Okay, this is live. I can't operate a microphone. I'm not that good at this stuff. Is there a case to be made on some of these for an undercut radii or a radii that kind of rolls into the main surface rather than the hard cut that we're seeing in your illustration?
Evoluted.
Yeah, I have some information. I have nothing on this about that, but yeah, it's probably something we can discuss later. So we can get together on that. But yes.
All right, thank you for that. All right. Hold on, there we go.
All right, so this was a cool test I did years ago. This is obviously a crankshaft, and what you're looking at here is some fixturing that is attached to it to measure oil flow from a main journal to a rod journal as this engine is running. It's a live running engine. The wires come out the front to an encoder. So we actually bolted this engine in and ran it in an engine. All right, so as we talk about, again, oil pressures, you've learned there's film pressures and so forth. This is all oil pressure, galley pressure. So this engine we ran at 3 different RPMs, 65 PSI, 60 PSI, and 55 PSI. I made 3 passes, that being the line right up there. This was an efficient engine as far as oil management. It was very specific NASCAR engine for that, and we controlled. So at 65 blue, 55 being white, at 8,500, you can see at the rod journal, we lost 36 pounds of oil pressure. So the concept here of what's going on is you're reducing oil flow, and to make more power, what's really happening? At 55 PSI of galley pressure, what you see in the car, at 9,000 RPMs, we lost 44 pounds. That puts it at 11 PSI of oil pressure at the rod journals. To add to that, I don't have it on here, I can show you simulation on oil hole design and location, because when that crankshaft is spinning, let's talk about a typical 180, a grooved upper shell, solid lower, typical. It's only feeding oil 180 degrees. I can show you simulation of the oil hole itself in the crankshaft that I can get 7% air between there or 70% air. All right, so now you calculate if you have poor oil design, thin oil, reducing oil, try to make more power. What do you really have here? Now keep in mind, we were just talking about crank flex. Now you're trying to fix this whole thing going on, 9,000 RPMs with 11 PSI. All right, so what's the fix? All right, well, be observant of your oil pressure. Our thing, this week, I've introduced the F-series bearing. It's a new bearing that Clevites came up with. I've worked on this for about 2 years. some of the features of it. There's more information in the booth. I have it. Ramp and pad design thrust. It's not new to a lot of people. To some people, it's brand new. The LS has a ramp and pad design on there. The ramp and pad, basically what it's doing is there is an area right here, 3/1000 to 0. This is the contact area. It's on every 2199 and 2411 LS bearing in the rear only. So if you ever put an LS in, don't sand the rear if you're needing clearance, because you eliminate that feature. By this ramp and pad, you get 93% more thrust load versus a flat, because you get two pieces of, if you get a crankshaft to a flat surface crankshaft and a bearing, you can't get oil in there. All right, this allows oil in there, so you get more thrust load on there. The other cool feature that I'm working on, again, this is new to the aftermarket. It is not new to the industry. MAHLE has had this. It's a tri-mil bearing, same cast. I use the same prints as the H bearing. It is a lead tin indium, so it has some movement, alumina, and it is plated. It's not a coated bearing, it is a plated bearing. And initial tests on this right now, I have more testing scheduled. A 90% increase in load carrying capacity of seizure resistance. So we're talking about the oil, films, flex, everything going on. This isn't the fix. This is just adding more margin. Again, I was a reliability engineer and worked on this a lot. Everything in my mind is about making more power, but having reliability. So this is a drastic improvement on there. So this launch is for LS, small block Chevy, big block Chevy, and the Godzilla on the initial phase, and more to come later point. But in fairness, it's a soft launch. I don't have parts, but just know, because of a lot of this has driven my push to get this out.
Just real quick, the electroplated is a coated bearing, right?
That is incorrect. Electroplating, every bearing overlay is electroplated. It's a positive negative charge dipped in a tank to electroplate. Basically, it's similar to how you would chrome plate a bumper. Electroplating is how we put the overlay on. A coated is a topical, and that is applied after an overlay. This does not have a topical. It is plated, and it will give the same characteristics of what you're used to in an uncoated bearing. All right, and so there was the platforms that I had just mentioned.
Okay. All right, so we're going to make a little change here, but everything that we're linking up to, for instance, just piggyback on what he just said, if you actually look at that bearing before, let me just bounce back to it just a second. The actual contact area is less than what we used to have. What he's been able to do is introduce film, oil. In other words, it's not making contact. A simple change, simple design has yielded a tremendous, like the tractor pull guys, I have a lot of fun with you guys, and you're just sitting there just killing the rear main, killing the thrust. This is a nice path to remedy, all right? So it's a neat way of changing, and this is new. This is cool stuff. All right, so let's get over to this guy. All right, crankshaft torsional loading and cause and effect. What we really look at, and I'm going to show that you have a first order balance, you have a second order. There's actually other multiples I'll talk about in a minute, but then it's controlled through damping, all right? So what I'm going to do is just sort of run into this discussion and say, there's different types of dampers out there, and I'm not going to sit there and say that one brand has over another. That's for you to decide. But I will say, principally, those are three most common. The one on the lower right, that's OEM, you've seen it a lot. The one at the top is basically a viscous unit. And then on the lower left, there is a elastometer type, all right? Multi-ring with different designs. The two at the bottom, the interesting thing about them, their Achilles heel to all dampers, by the way, is thermal. In other words, you're guaranteed during the cycling, and start the engine, that bad boy is generating heat. Now, if it contains the heat, there's a major problem because, first of all, let's just simply call it, elastometer, but let's call it a rubber band. Let's keep it that simple. It doesn't like heat. It doesn't like to be changed, but it's inevitable from the time you take it off the shelf and introduce it to the application, it cannot get better. I think I used a coin yesterday, it's not like wine, it does not get better with age. So, in this particular though, the manufacturers will tell their story. But of those designs right there, the only major discrimination difference is also the fact that relieving thermal is an ace to longevity and stability. Just keep that in the back of your mind. Now, I'm going to show you this is a very common issue that you have, all of you guys who balance and use the harmonic balancer as a mechanism of correction. This is all in the first order. You notice all the holes. Anybody drill their cranks like that, or the counterweights? Excuse me, dampers? That was a Biden moment. I'll get over that in a minute. So, the bottom line is I just want to say that when you see this, and I used to even see it come out of the OEM, all right? And when they would introduce that, I also noticed a trend line that, and we've all seen the dampener rotate over cycle time. You know, whenever we do the old timing, that thing would be out of position and say, wow, what's going on here? Well, it's obvious. What happens is it creates, you gotta understand, the inertial ring lives in its own environment, right? It's different than the hub. The elastometer that's in the mixing the two together takes care of torsional twist. Now that's my design process, the engineers have it, but that OEM unit there put into a race car is just suicide. It's outside. Remember, this guy was supposed to be some guy running down the road, and every now and then he'd get on the throttle, but it's not a race car. Not even close. That right there causes offsetting forces that will actually take and compress on one end and stretch on the other, and the bonding agent will surrender. Okay? And one of the reasons it surrenders is because of thermal activity. Now, within the scope of that, we touched on this a little bit yesterday, we get a issue where we'll have metal exchange. Everybody's done an engine, pulled a harmonic balancer off, and you'll see parent metal from the damper hub to the crank. Now, in order to get there, that means it had to get up to temperatures in excess of 1500 degrees Fahrenheit. That's a problem. But it also is testifying, it's yelling at you. I can't do my job. I'm the wrong design.
Randy, 1400, 1500 degrees. What we just talk about overlay temperatures? 360 degrees, lowest melting point. All right, so you're inducing 1400 degrees into the shaft. Now you're expecting the oil to dissipate that heat out before you start melting the overlay out.
Yeah,
so another issue.
Not only that, a lot of times when we read bearings, sometimes we see trends and differentials of location. And it always puzzled me until I started backing into it and saying, why is it different? Well, amazing enough, the bearing surrenders the heat, just like the elastometer. So when you're seeing these targeted issues, not the crank manufacturer's problem, it's the damper guy. Now, those guys have cookie cutter pieces, but what you really need to do is come back and do some little one-on-one time with engineering. In other words, if you're making 4,000 horsepower, don't treat it like it's a 265 Chevy. Now, unfortunately, a lot of guys will call up and they'll call the vendors and say, hey, I need a damper. He says, well, what cubic inch are you? Well, I'm this. How much horsepower? I'm that. Well, that probably isn't what it's going to run. Now, and a lot of times, unfortunately, the salesperson you're talking to, he's doing his job, selling product. What you really need to know is get the technical side of it and find a solution to your problem. This is what exactly we're looking at. You'll see that the rubber, I'm going to keep it that simple, over time has to fatigue. It has to surrender. There is, you can, I don't care what you can take it to church with it, you can pray with it, you can even send money at it. It cannot recover. All right, so crankshaft torsion caused by combustion and torsional loads. I'm going to show an animation for you guys, don't get nervous, this is a diesel crank, but I do that because it's really a great visual as to what's going on. And torsional load, and you'll see it'll attack into the radius area primary, but you'll see it's not one single pulse. In other words, as you generate activity, this thing is just spreading out the free end of the crank now. That's what the damper, that's what it's highlighting, trying to control that. But there's a point in time as these things run on, or cumulatively, they have so much force the damper says, I quit, I'm done. All right, so again, this is where you have to start rethinking how you're building your engines. All right, let's see. Well, so what I did here is I did a capture. All right, that boy is just, and this is a technical term, pissed off. So at the end of the day, you got to appreciate what's the remedy there. Well, the remedy is, and I know you guys are going to hate me for saying that, make less power. There's not a person in here who's going to go with that. So at the end of the day, you need to control the power. And that's through process of materials and design. The crank manufacturers really have their hands full figuring this thing out. And the primary reason is you make so many different applications. You know, we had the animation of flex up there, and I presented that in a couple of different presentations. And the guy said, oh, I can't be like that. I said, you've never seen top fuel, have you? So, I mean, these things move and wiggle and do everything. And by the way, they have limited cycle life. The top fuel guys have found ways to navigate and entertain us at times. All right. But keep it down to here, a little four-cylinder. That's exactly what's going on. So it's not a big diesel crank. Every engine that you start up has torsional load. That load is looking for something to stay stable. Call it resistance. At some point it surrenders. Well, if it surrenders, here's the thing that's interesting. The counterweight takes on its own identity. Got it? Okay, where's our mic?
Hopefully I can be loud enough.
Well, they're recording it, that's their requirement. They're kind enough to let us do it, so we try to honor them.
Are we on? It is on?
Not yet.
Not yet.
You were right, you were louder than the mic.
Now,
There you
Yes.
go.
now I'm on. How do so many flat plane cranks get away with no harmonic balancer at all?
Oh, that's easy, they don't.
Most motorcycle engines don't have a harmonic balancer.
I'm sorry, one more time.
Most motorcycle engines don't have a harmonic balancer.
Sure, still got the same problem. Harmonics are related to an excitation frequency. The problem with a flat plane is there's not any cross cancellation. So a lot of times in the motorcycle is, again, well, let's do it this way. Guys used to come to me a lot with Harley Davidsons, and they would say, hey, what's the magic formula for this thing? I said, there's only one that I know of. They said, what's that? I said, buy a Honda. So you have to understand you're going to hit a sweet spot. Now, you get some really high RPM stuff, and I guarantee you let me go ahead and measure it out there, it's not as smooth as you think. It's just short-term, dribbling, drag racing. By the same token, if you're a flat plane or a cross plane, and the motorcycle guys, that changes the torque characteristics of that engine profile, which, by the way, makes less power. The cross plane will make less power overall.
Right.
But the torque curve applicable to that is much smoother. So these guys are in road racing, come around the corner and they screw into the throttle. When it's tight, the wheel comes off. What do you think is going to happen in a turn? You have a new fresh marker in your shorts that's going to take you out of the game, right? Well, by changing that, they've compromised power for torque curve. Now, I'm trying to come back to your specific, and that is there's still harmonics there. A lot of this stuff, by the way, is not as bad because of the valve train, overhead cam, less moving parts. As we take more and more parts out of the system, we have less parts that become excited. All right, spring rates, all that's totally different animal.
So you're saying that the valve train harmonics affect how much the crankshaft flexes?
No, the flex is power related.
Okay.
All right, the flex is a distortion from rotation to orbit. That does aggravate first order. Now, I'm going to go into this in just a second, but what does happen is the counterweight mission the primary mission of the counterweight is to offset the mass of the piston rod assembly.
Right.
That's primary. All right. The secondary is it is also a torsional damper in its own right. We call it a flywheel effect because of the mass will slow down things. All right. The other side of that equation is that it needs to be consistent. What we're seeing with RPM, and we're going to go into drilling what compromises that in just a second. I think it's going to answer your question a little better. So I may have got too far to the left of my discussion, but I want you to appreciate, I want to make sure I'm answering your question to your satisfaction.
Okay.
Close enough?
Yeah.
Okay. Hey, Chris, when your honorary push button, when you hand that over, that might help everybody. All right, so you want to pick up on that, Nate? Or you want me to
Go ahead.
All right, go ahead. All right, here's the bottom line. As that crank flexes over time, it will surrender. Now this is basically a picture of MAHLE. It's an AC image, but you see all those bright lines, that's a torsional surrendering of the material. It basically is cracking, just that simple. Let me do it one more time. You see, now this is a different perspective, but once there's a crack, it won't get better, right? How does that happen? A lot of this is out of not first order balance, but torsional relation balance. But unfortunately, they all come together, and I'll talk about that in just a second here. Here's what happens if you don't pay attention. You get 2 for the price of 1, all right? Now, there's another example here, and this is a twin turbo, 2,000 horsepower, and again, price 2 for the price of 1. Dan and I talked about this over a different time. We say, why is that happening? What's going on? Because sometimes, or I'll say 70, 80% of the time, in that application, I see it snap on the rear. But occasionally, I'll see it snap on the front. What we think, and I gave key word here, think, is this is because, now these happen to be the drifters, all right, the guys that are out there entertaining everybody. But the deal is that we think that the rev limiter is the cause. And that is because it gets out of firing sequence, and the cylinder is basically unloaded and loaded at the wrong time.
And Randy, I can jump in. And remember, rev limiter, you're cutting a cylinder out. So as one of the things we're talking about, the pressures and what's happening with the firing is now you're killing the cylinder twice, so you threw the rhythm out. So every time you know, and I've had some issues with 2 cars, identical builds, different drivers, in this case team cars, one had an issue, one didn't. And the conclusion is one was a drag car, one was a drift car. And issues like this, and it was driving style, how long they would stay in the rev limiter. When they went through the water box, how long they stayed in there and how hard they were on the rev limiter. End result, same cars, same builds, one continually had problems, one didn't.
Chris?
Right behind you.
Right behind you. There you go, see?
There you go.
Got him trained.
In the case of drift car, would that have anything to do with the way those guys are on and off the clutch too? Wide open throttle, hammer the clutch to get into a drift and then come back off it? You're putting a huge torsional load on the end of the crank.
Everything is relative.
That's right.
Everything is relative. In many cases, it's not one thing. It's a stack up of this is to the limit, that's to the limit, and the stack up of those threw it over the limit.
Yeah. The other linkage happens to be with narcotics or alcohol.
Randy.
Sorry, went too far. One more time, hand the mic, guys. See, you're gonna hate me before the day's over. There we go.
Check.
You're good?
Okay, so talk about the difference between a billet crank and a forged crank. I would think the harmonics are going to be different, which would necessitate different tuning, if you will, on the harmonic balance.
Fair question. Everything is different. No 2 items are ever the same. And I can change the frequency, not just by the alloy, but by the configuration. Now, I will simply say, and I think I won't get an argument here, billet cranks are a cheaper way to process a crank. Forged cranks are more costly, but I guarantee you they're stronger.
Which one? The billet's stronger?
No.
Forged is stronger.
Forging is always stronger. Always. And I guess I might get some hate mail on that one, but I'm going to simply say I have never done any durability testing and actually stress test the 2 materials, process of manufacturing. And the reason, and one of the things is when you're in a billet, it's a very unique process to make the core, and that's the base material, because differential of density, hardness, machinability, all those things change depending upon the supplier. Forging can have that too. I mean, anytime you have a process, there's always a variable. It's generally human influence. But across the board, I think I can make a safe statement and say forging will win every time. But you pay more. All right, got one way back there. Uh-oh, here we go. Come on up.
Got a question about pressure versus volume. So we do drag and drive events. I have a standard volume, high pressure pump of mine. Ran for 5 years. We pulled the main out of it. Bearings look perfect, no problem. We ran high volume and had issues too. Is that anything to do with like heat transfer from the bearing?
There's a lot of variables in that. I mean, we have to really kind of break down the engine. Clearance is what oil you use, not brand. Brands can be, but you know, what weight oil and so forth. There's a lot of variables. That's not a simple run this or run that when you start adding performance. So you will get some different feedback on that. Again, I stay in my lane. I'm not a oil pump guy. I'm not a crankshaft guy. I'm a bearing guy. But to me, I look at flow. We calculate in any bearing how many cubic millimeters of oil flow it takes to go across that. When you change that, as first pictures had, when you add power and stuff like that, it all changes, and some of it just is experience of feeding that, because the testing to support that is inconclusive on that. So I hate to dance out of that question too much, but anybody knows me knows if I don't know, I'm going to tell you I don't know, because I will never say something that I don't firmly believe and have data to support that.
And there's too many variables in the way you presented that. Not that you didn't present it the way you've seen it, but
Right.
God, need a lot of data to even attempt to come to a solution. But generically speaking, here's where I'll come back to. No oil, or bad in the story. So pressure, volume, however it delivers to the bearing surface, as long as it's got film, it has a much better chance of survival. You take that away, you're done. How it gets that film, that's really where your question is core. Okay, so I'm with Dan. I could guess all day long and miss it, other than simply say, trial and error on your part is where you finally got to, I think.
And to go with that, I recently had a conversation with MAHLE, and we were looking at doing some collaborative, kind of like me and Randy did here on that topic, and trying to come up with some more hard data. Maybe next year we would have some more information on that from an oil pump and the bearing, and tying that all together here.
Thank you.
Thank you.
Thank you.
By the way, this road show we got going on here is only going to get better. We keep learning every day. This thing, what we think we know, we don't know. Oh, here we go. Where'd that thing go?
Is this thing turned on? Obviously, I don't know how to do it. Within the context of this damper stuff, is there any particular reason other than long habits why we have the damper in the front of the crank when all of the work and all of the vibrations are happening through the middle and between the bearings? Is there an opportunity to have a damper further back on the crankshaft and do a different or a better job?
I'm not trying to give you the right answer on that, but like in Formula One, we'll have as many as 9 different dampers on an engine. All right. And so what we're trying to do is identify the excitation location. And from there, those dampers are then tuned for the specifics of that application. But Formula One, unlike us, here we count our money, Formula One weighs their money. So, so you got to understand there's limitations, but we put them on the free end because it's a logical place to be. But you have to appreciate the drivetrain relationship, flywheel back. It is a contributor to the functionality, right? And so, believe it or not, a conventional clutch disc that has the spring in it, that's a form of damping. The guys that do the rice rocket stuff that typically already, first of all, they're flat plane, right? They second order vibration, which I'm going to get into in a minute. Then they go ahead and do a multi-disc clutch that is solid. And you're talking about putting the salt on the wound. That's exactly what they do. And that transfers all the way back to the ring and pinion at the rear of the engine, because it goes through, it'll actually fret the gears, right? So let me move on to, unless there's another question. We good? All right. I want to talk about this one for a second, because it's pretty common that we'll see because of OEM manufacturing limitations. In other words, all of us have heard or seen or witnessed external balance units. And I think that guy is nuts, pure and simple. Should have never happened. But it's done because of means of economy. In other words, they didn't have enough material inside of the crank bay area to put enough counterweight in it. So what they did to save the process and keep the engine within scope of cost, they went external. Now, GM did it, Ford did it, a couple did Pontiac, so forth. But the point is, it is here to stay. Well, let me tell you, one of the problems with that, I'm going to use this example. Let's see if I can pinpoint from here. This happens to be a Ford application, right there, 28 ounce. That's 794 gross grams sitting out the free end of the crank. All right, offset. but it works cumulatively with the crankshaft to balance in the first order. But it being what I call the free end, that thing's out there like a flagpole. The faster you go, that counterweight takes its own identity. Total different function. And then when it's captured inside of the snout or the free end, how do you want to put it, depending upon the interference, that unit will have a tendency to fret more than anything. All right, now, what happens though is that unit at 794 grams at 6,000 RPM will generate 1,790 pounds of force all by itself. All by itself. So when you go internal, you're taking that out of the equation. So it's helping the crank to not go through this gyration. And that's really what's happening. Now, at the end of the day, a lot of the Ford guys, and I'm not here to pick on them at all, other than the fact they got a 28 ounce in, but they put a 50 on there and send it. Well, the problem is now that 50-inch unit now generates 3,195 pounds. But it interchanges, bolts on, and think what the crank sees. It's going to start talking to you in biblical terms because it's going to surrender, all right? So over here, what I'm really trying to get is this interface between the two. Just at 6,000 RPM, you're getting a tremendous amount of offsetting force that's unsupported. Keep that clear. You say, well, wait a minute, what about the flywheel? Isn't it doing the same thing? By force, yes, but proximity or leverage distance, if you will, is not as aggravated. And it's also typically a larger mass as opposed to a snout down here that might be inch 300, we got a 3-inch ring on the back. So you can see it's just a matter of exchanging load and displacing load. Bottom line, it's still a bad idea. And here's what happens, guys. Threading, these are main caps. Now I got a series down here. I'm gonna go right over here on this side and just simply see, you can see metal exchange. Any of you guys ever take these things apart and you notice the caps are loose? All right, it's surrendered through the harmonics, right? That causes the fretting. And so that literally will reshape the units. Now, let me see if I got another better picture here. When we blow this thing up, everybody has loose caps, they'll come in and I'll put these little dimples here. Anybody do that? Okay, shouldn't do that. All right, now as soon as you do that, it's dead soft. You'll put the cap on, you feel good, it seems secure, and you run it. As soon as you fire that engine, that thing surrenders. You know, too late, oil pan's on, it's down the road. So, well, the only way to fix this is remachine, re-register, and change your fasteners by quality. In other words, you want to increase your clamp pressure and get rid of that external balance. All right, here's where we get to have a lot of fun.
Yeah, so what we have here is, this came out one engine, this is an LS engine. And as we were talking about the crank load, crank flex, what's happening. Both these are, this is number 2 and number 4 out of the same engine, LS. And you can see it's an upper main by the groove, right? The interesting thing is you see, obviously the load, the force is going up, right? Which we know the force is going down until the crank flexes. Interesting enough, on this one here, you can actually see the arc as it's coming across is how much flex it's going. It is actually coming around like so to make that kind of a wear point. Front one, same. You're seeing it on the upper, number 2 and number 4 on that, on a typical LS. So this is, again, 2 uppers. If you look at, they're getting contact up here in this area on the upper to the point of we have went through the overlay and we wore through and we're starting to see the substrate starting to show through. So at this point, once you go through the overlay and you're into the copper tin lead substrate that we talked about, once you get into that, at this point, the frictional temperature is escalated because now that is not designed to hold that kind of load pressure from that. That's why the overlay is on there. So again, this same picture, what's supposed to happen in those 2 cases, this is what's happening. There's the bearings to show you're getting minimum oil film right here on the top because of crank flex. These pictures are from one of the nitro cars. I love the nitro cars because I can take 1,000 feet and I can simulate exactly what happens on other cars in years. I can do it in 1,000 feet, so thank you guys back there. So, but in this case, again, you see crank flex. There's the upper main, lower main. You can see, in this case, this half the bearing looks good. That half bearing looks good. All right, there's that much flex that it is just loading one side of the bearing. In this case, because of flex and orbiting, it is worn completely into the substrate. All right, in this case, insufficient oil, it's got the whole bearing going on. If you see the black that's in here, at this point, it wore through the overlay as mentioned. Substrate does not work good as a bearing material, it's support. And at that point, the frictional temperature, it got excessively high. That is coked oil. And when you coke oil, it is not lubricated. It creates its own heat. You're baking the oil into there to the point of it is wanting to seize. This particular bearing is really getting bad because out here on the edges is contact always in there, and we talked yesterday about some failure modes of bearings closing in. Next thing you know, this bearing would want to grab the journal and start spinning. Again, self-generating, just kind of reiterate, you're taking this space, and anytime that shaft isn't where it's supposed to be because of flex, balancing issues, extra things going on, as we discussed, this pressure doesn't always go down, it's going everywhere. Thin oil film, simply back to the same thing. When the crank starts orbiting, you get thin oil film, and this is a mild case of just it's running out of oil and you're creating enough frictional temperature. When you start, when it starts swinging out, usually that's when you see on the overlay, you'll see some dark coloring, like some black in it, and that is the components melting out. Excessive bearing clearance. This is, as you remember, I talked about when the bearing is pulling away from the rod. The more clearance you have, the larger that negative volume is. Simulation and the bearings I showed, the larger it is, the longer it takes to recover from that low oil pressure, and you get, because of excessive clearance, that will show up point load exactly like the simulation and the bearings that I showed in the previous slides. Just by the oil clearance you run, not having the right oil clearance with the right oil. Cavitation. Cavitation is heavily dictated by, typically it's on a longer run engine. Cavitation is when that bearing pulls apart and creates that negative. It creates an air pocket. The air pocket then, as it grows, it implodes in itself, and when it implodes in itself, it causes erosion in the overlay. And repeat it over. It's the same thing as ultrasonic cleaners. If anybody has an ultrasonic cleaner, how's it clean? It does it by vibration, creating bubbles. The bubbles implode, which is also the same thing. A lot of blocks crack from cavitation of the water system from the piston slapnet, creating an air bubble that implodes in itself and eventually erodes enough to crack the block. That is the same thing that's going on in an oil bearing, in the oil on a bearing as it separates apart.
One of the major causes that we find it now, certainly if you had aerated oil, I mean, there'd be a whole bunch of reasons, the way you're picking up the oil pump system, whatever, that's a different discussion. But one of the catalysts happens to be because you open a clearance. As Dan just said, once you allow, you have to, the best example I can think of, every one of us has probably pulled a dowel pin out of a block with a slide hammer, right? So just envision that pin and bearing have clearance and it's just being pulled, and this is really quite fast, by the way, and I'll talk about it in just one more second. But what we're trying to get to is get you to understand, if you aerate the system, because of the cylinder pressure that you have, and in this case overlap, condition that you generate, it literally does make it a sonic cleaner. And then if you studied anything about sonic cleaners, it's impressive what they can do. Well, that's not the mission statement of the engine, right? So you got to understand that this deal is, as you open clearance, you're adding a variable that has penalty. Now, I got different people of different size engines running excessive clearances, and I'm going to touch on that a little bit more. But the point I'm trying to get to is cause and effect. When we see this kind of stuff, that's not natural. That is an event but it's been created by the environment. So let me show you this. We're going to show how this linkage comes into. And so when we talk about balancing, we have a crankshaft picture at the top, and then we have a silhouette image on the bottom. I'm going to try to explain and keep it as simple as I can here. The yellow units right here, that represents weight. All right? The center, the CG, what we call the center of gravity, and then there is the principal center line of axis. In a perfect rotor, where you'll see on the right, I've got a unit of weight here and a unit of weight. Those two, I don't care if it's 1,000 pounds in both directions, they will establish a CG moment. All right? If those units are different in weight, then that CG will move off center, creating a rocking motion. Now, as you increase the unbalance, you generate a lot of force, which I'll show you in a second. But when we look at a screen, for instance, in a perfect world, I want to see one side, top dead center, the other one, bottom dead center, or 180 degrees of compensation. Just think of it simply as a seesaw. If the seesaw is in there, well, some of you guys are old enough to remember that, and you young guys, there's no apps for this. So the deal is that when you put a plank of wood out, you put the pivot on, if you put equal weight, equal distance, I found out as a kid I could hover, right? That's pretty cool. But when one guy leaned, he changed the moment center, and we would rock back and forth. As simple as that is, we call that term coupling. So what we want to do is find out what's the benefit. Now, this is under the ISO standard, but I'm going to show you that particular application. We entertained ourselves here, by the way, but it's 0.02 grams of weight. As we go down, you can see at 1,000 RPM, there's nothing there. This engine is as happy as it can be. At 10,000, it's only 0.37 pounds. You know, listen, this is good stuff. Now, that is an optimum situation, but it's also an entertaining tally that I put up. Now, this is what it would look like if you look at right side, left side, and center. So you can see I'm 0.3 grams here, 0.02 on this side, and the center of the crank I'm 0.027. This is one happy puppy. Now, that's not how you guys do it. What typically happens here, I'm back to my 2D again, I've got a unit of weight now that is not canceled, but I'm making it somewhat proportional. And you notice the CG moved over. So now I've created a rocking motion within the engine. Now what happens here is that if I go back to the screen, and this, by the way, was a crank kit. We just pulled out, and by the way, it said balance. That's the fun part. On the left side, it had 33 grams of unbalance. Right side, it had 26 grams. But I want you to notice this is at 264 degrees. This one's over here at 53 degrees. But look at the center, it's at TDC. I have 3 load moments taking place in a single rotation. I want 1, not 3. All right? And now what happens, even though it's 26, 33, I got 17 in the middle. So here's what's interesting with that. Now on the left side here, based on that 33 grams, I want you to take note that as we increase RPM, the mass of unbalance does not change. However, the force generated does. For instance, I'm out here at 1,000 RPM, I got 7 pounds of force. Down here, I'm 740 pounds of force. This number is what's really important to you. At 1,000 RPM, that 7 pound, I'm going to call it a hammer, is hitting 16.6 times per second. When you go down here to 10,000, that's 166 times per second. This is simple math, and you can't beat it. But here's the way I'm going to explain this. If I stand out here, I take a 7 pound hammer, put it right here, and I take a 740 pound hammer, and I let it go right above my feet. Newton says they're going to land at the same time, right? Here's the question to you, which one hurt like hell? All right? Well, that's what the bearing sees. But this is what's worse about that. It sees 166 times per second. Think about it. 166 times per second. Okay, so you run a 10-second car. 1,600 times per second. Or excuse me, during the durability of 10 seconds. So, but that's on the left. It has its own individual vector load. Here's the right side. Now it was only 29 grams, but the same gig. 5 grams down to 590, but always the same frequency. You cannot violate that. But then in the center, I only had 3.84, and then went down here and it's at 380. I've got 3 events happening in a single rotation. That's outside the scope of what we call first order balance. Now, back here, we're just showing that when we do this, I need to jump one more forward. There we go. It starts to add a problem. All right, now this is a what we call a waterfall graph. And it's a little confusing if you haven't looked at them, so I'll try and do my best to tell you what's going on. The red graph right there, excuse me, line, and you'll see there's an intersection. That is what's called the 4th order of unbalance. Then there's also the 3rd order. The 1st order, by the way, is way over here. It's really quite okay. It doesn't have a problem. So what causes the 4th order is every time we fire an engine up, within 360 degrees, we have 4 pulses, or 4 loads. Not 8, 4. Now, if we go 720 degrees, I have cumulative of 8. This application here is a 571 cubic inch big block Chevy, blower. And on the 8th order, right here, they finally get to a point of being really, really pissed off. Now the harmonic balancer, if it's tuned there, it should put that in check. If it's down here in this lower area, it's a waste of time. So one size cannot fit all. So what I'm after is, first order, that's what you do typically on your balancing machine. The multiple orders are controlled by your damper. So what that looks like here is that, again, try and make it as simple as I can. At 6,000 RPM, if I want to know, divided by 60, that's going to generate 100 hertz. There's 4 power strokes. Simple math, 4 times 100, 400 times per second at 6,000 RPM. But remember, I supposedly only have the first order being add 1 time. In the example I gave you, I put 3 more into it. And this is what takes the counterweight and drives it nuts. All right, so as we go down here to 10,000, I got 10,500. I use that because Pro Stock seems that's where the rev limiters are. That's generating 700 cycles per second, or torsional pulse, 42,000 times per minute. So you can see that over time, you keep beating on something long enough, I would use the excuse, a little baby with a little hammer left in a room unattended will destroy the room. Well, that's what harmonics are. They're that little baby with no control. That's exactly what's going on. Now, we're going to sort of move up a little bit and say, functions of counterweight. Counterbalance rotating mass assembly, number 1, add structural strength of crankshaft. Believe it or not, that is an important part of the equation for giving it strength. Add torsional control. If the bob weight is not being satisfied by the counterweight, it has its own mission activity. Its mission was to counter that. But when it's out of balance, it's out of control. But it also maintains shape and rigidity. Rigidity is a key part of the equation, because as I open clearances in engines, it's no longer rotating, it's orbiting. Now, I've got guys running as much as 6, even 7 thousandths clearance on mains. Anybody doing that here? See, there is God. Okay, good. The bottom line is, that means if you give it clearance, it's going to offset. So if the average assembly is somewhere around 70, 80 pounds at 10,000 RPM, it generates a force of almost 2,000 pounds of unbalance all by itself. But when you were on the balancing machine, when you balance it, you were spinning it on center. Then you put it in application, you just threw the entire thing out of balance. Now, there's a whole bunch of reasons why people have done that. We're going to touch on that in a second. But we're going to simply say most people drill cranks, right? Pretty common, easy way to do it. You notice this particular example, proximity, you see how close that is? There, and also drill, we call it a China syndrome. They do, and then this guy here is insane. So a customer sent this to me, he says, what do you think we ought to do with that? And I said, well, there's only one thing to do. He said, take it out back, dig a hole, salute it, and thank us for its service. It's done. All right? But that counterweight cannot be doing its job. It is fluttering. Fluttering is a key word here. Now back here, we want minimal holes. If I had a perfect world, I'd have no holes, just to be honest with you. But anytime I drill a hole, I change the shape of the counterweight. I'm giving it a reason. For instance, right on the edge here, and all of you have seen it, where the drill is offset and it's actually compromised. What you're doing is segmenting that counterweight. You're asking it to have a different identity and process. So you are the guy creating the problem. Now there is a remedy though. The remedy is software is available right here for cutting it down on the lathe. We'll be glad to show you that at the booth. And by the way, you get charged for that stuff. And by the way, I do believe that's why you're in business. So we can give remedy and we can make margin. So that's good stuff. But it looks something like this. A typical crank counterweight, eccentric especially, is what we can do is we can calculate the amount of load, in this case 106 grams, and we can tell you how much to cut off that counterweight. Just math. It's just we do it well. Torsional control, as cylinder pressure and torque increase, crankshaft journals are twisting as much as 2.5 degrees end to end. You got to understand, when they're running, that crank actually lags. But it's also doing this. That's what's causing a lot of panic, not panic, excuse me. It actually is panic to the rest of the engine. But what happens is that vibration is going from the crank through the rest of the engine. So it terrorizes everything else that's related to it. 8 counterweights. I'm an 8 counterweight guy, I just got to tell you. The reason 6 counterweights were developed is means of economy. The first units I ever built were 8 counterweight. And then the beam counter got hold of it. He said, no, figure it out. So what we did is we did offsets to sort of trick the center of the crank. Bad idea, driven by economics. 8 counterweights is the right way. All right, rice rocket stuff. Every guy knows, and they've heard this, that if you make the crank light enough, it'll rotate faster and slow down faster, and that sounds true. It also compromises the integrity. But more importantly, whenever you're talking about a flat plane crank, you have just screwed yourself. All right, because that unit had harmonic problems, and you just aggravated the hell out of it. Those counterweights, our primary mission is to offset the piston rod mass assembly. So if that equation is done by the OEM and you decide to lighten, what do you think happened to the equation? Just went south. Will it run? Absolutely. Will it run long? Nope. All right, just got to put that in perspective. Now, a lot of guys, and again, lightening is always important. You know, by lightening the mass, you know you can accelerate, decelerate, you change the moment of inertia. Great idea, I believe in it, right up to the point that you compromise structural integrity. By doing this right here, I guarantee you this unit has met the criteria of having offset mass for the piston rod assembly. But what it doesn't have is the ability to maintain integrity of shape. This is very popular. I'm something to really like, guys, and I think it's the coolest looking thing I ever saw. All right? And I know the intent behind it. I'm just simply saying we're learning now that, man, we want to rethink this a little bit. We want to come back and think. Now, I'm not saying it's bad. I'm just simply saying there's opportunity here for misbehaving of the counterweight. This is my pet peeve right here. We talked about it earlier, and Dan is actually, I'm going to let him pick up on it. Right there.
Yeah, so as we talked earlier, the illustration with the polishing, so changing, 2 things happen on this. Changing that oil hole, again, changes the feed that it's feeding to the journal. All right, so saying, oh, I'm gonna add more oil, you can actually be a negative effect by taking that hole and going to the point where it will decrease the oil going in there. The other problem is, as the crank goes in there, I don't have it on this presentation, but I can actually show you data on that where the film pressure gets smaller right after that hole. So you're increasing right after the hole, you're decreasing the film pressure to the point of you can have a bearing wear because of adding that oil hole there. So, you know, it's a great concept. I did it, you know, because you're always saying, oh, it's going to add more oil. The reality is, again, this is not the same engine, so the effect of that downstream is you can create an issue. To the point, if you look right past the arrow on the left, thank you, Randy, you can see the polishing of the crank. All right, that is actually where it's contacting. So this fix is self-induced a bearing issue. You can see the polishing on the crank of actually where it is making contact just by, now, did you see it right at first? Probably not. I didn't at first either. All of a sudden I'm looking at it, it's like, oh yeah, just even the crankshaft is showing the wear right there by that added feature to try to make it better. Made a problem.
What that really does is it's taking the science out of the primary design engineer and you said, okay, you're not as smart as I am, I'm gonna show you, and I'm gonna open this up so I can get around the corner. Wrong. What you really have done is you sat there and aggravated an environment that's already been designed by engineering to spread the oil to get the oil film. Remember in the beginning we showed at different RPMs, we're seeing how oil film can be moved around with speed, with flexure. Well, this right here, and Dan's 100% right. I think everybody in the room that's ever touched a crank said, I can make that sucker better. Well, I gotta tell you, those days are over. You need to really come back and rethink where you're going with that. And I'm gonna tell you that unless you can have the ability to measure, I wouldn't touch it. I would surrender all of that to the OE. I would not violate this process. Now, let me go back here though. Arrowwing, John Calley is a really neat guy if you ever get to meet him. He came up with this design here and he's thinking, well, as the oil is being pumped here, it's gotta go somewhere. And what we don't wanna do is reintroduce it back into the cycling area. So what he did is he sort of developed this Arrowwing design, and the intent is to redirect oil and direct it way back towards the mains, right? Now, that being said, John told me, he says, I think it's a pretty cool idea. He says, I can't really tell you that there's gonna be net benefit, I can just tell you it's better than not. So, that's not really interesting. We're now actually able to study that. And Ben Strader from EFI, if you guys go to a seminar, I get to talk to him, he found some stuff about this, and we're sort of investigating and finding out which is better. In other words, do we have knife edging or, well, this is another case. These are MAHLE inserts. Notice the width of the counterweight? And so we're trying all sorts of things over time, but here's what's wrong with that, right? That intersection right there. I guarantee you that that unit becomes live, and it will sit there and stress right there. You guys ever seen one of those? Now, you won't see it much more because it didn't work. All right, so this is what's coming to your theaters in the future. You're gonna start seeing a transition, I believe. It's been done in Europe for over 10 years. Those are bolt-on weights. Every racer in said, oh no, you're not gonna do that to me. That sucker comes off, we'll find it in the next zip code. Well, you gotta understand, the capture point here is easily calculated. We know what force is there. And these units here mean I can lower the diameter of the radius of application. So my windage just went way down. My polar moment came right up. My moment of inertia got better. All cool stuff. But old tales make us not jump in. But I'm telling you, this is going to be coming to theaters in the future. Now, here's another view of that. Sort of clean looking. But here's the best part. Tungsten, which is basically we call a trade name MAHLE, is much denser, so we can shorten these, but now we can go back here, and what we've always done is we put lightning into the rod throws, and we move these things around to get away from oil holes. Guess what? We've created a stress, okay, got it, and when you're making 100 horsepower, who cares? Make 1,000 horsepower, I start getting attention. Make 2,000 horsepower, I really get your attention. Make 3,000, I get 2 for 1. There's a point here where that will surrender. So this design here has, and this is my belief, and so I can't do anything other than say that. The crank guys in design, they're a lot smarter than I am. I'm just trying to tickle their thought process and say, why not put some strength back here because our load has gone exponential. What we're making available with boosted horsepower nowadays, incredible. Again, if the crank could talk, well, it wouldn't be good. You know, you'd have to wash its mouth. All right, so just understand it's headed this way. All right? Crank kit, one last thing here. This is an out-of-box situation for you guys that are actually in the crank business. This thing said balance and tolerance of 208 grams out. Right side 221. If they sent it out of the vehicle, if it went 10,000, which by the way it wouldn't, but it'd have 3,900 pounds of force, we call that a fender swapper. All right, so the deal is it would cause so much trauma. By the way, it would run. I guarantee it'd run, and you could rev it up. It'd be really entertaining, sort of like a vibrator. But
Randy.
Went too far, sorry. The point is that you got to understand this is what's going out in the marketplace. No disrespect to the crank manufacturer. You got to understand when he builds that thing, he has a target bob weight. But through the supply sources, whoever these guys are taking this thing, mix and mash and send them out the door, they're not even close. All right? So the deal is, I've always made this statement for the guys that are in the crank business. I always tell the customer, I don't care who he buys it from. If you just go to the client and say, look, it says balance, I want it balanced, you want it balanced, so here's what I'll do. Let me spin it up. If it's balanced, I won't charge you a dime. If it's out of balance, we need to catch it and fix it. I have never paid for a crank balance. Never. All right. Back to this one last thing. Load, 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 and everything that's going on here is now deflecting. We're making way too much power. That's what we do. But this cannot live in that environment for long. Again, I told you earlier, the only way to get rid of that is make less power. Non-starter. This right here is something we need to take a look at. So with that, I hope I haven't hurt your feelings anywhere. All right. Dan, closing comment.
I know your time is valuable, guys. I know we ran over a little bit. Apologies for that, but hopefully you found it valuable. We're available. There's nothing in this room, I was told. So Randy and I are here forever until the questions are answered. Feel free to stay, whatever. I was instructed by PRI, if you don't mind scanning the back of your chair and tell them how great a job we did. You can lie if you need to. So, feel free to stop by the booth. Randy and I are both in the booth. Feel free, open forum questions, whatever we have. And again, thank you for your time. I know it's valuable at this show with all this stuff. So.
I'm going to do this, and he told me not to.
Oh, geez.
Ready?
Nope.
He always goes back and tells on me. I'm going to ask a favor of everybody in there. Everybody got a phone? All right. Would you mind taking a picture of this clown? I mean, this guy? No, I'm serious. Would you guys mind where you're at? Grab your phone. Now, I realize I'm bending the envelope here. Okay, so now if you take all those pictures, take them home, put them on your mantle so you remember us.
Send money. So the reality is, I had to calm Randy down a little bit because Randy said, oh, great, well, we'll see how many people are left, and then everybody got to come in free and hopefully learn something, but to get out, you have to pay.
Yeah.
That's the catch.
Listen, we want to thank you guys, and I got to tell you, this is the fun part of industry, and that's because the change, all right? There's more stuff headed your way, and you need to talk directly to engineers, talk to the manufacturers. They're willing to share a lot of data. You make good products, but you're going to have to make them better. That's the gig. There's no way to get around this. And I'm hoping that between Dan and I, we've been able to tickle some thought and send you back out with a little bit more steering currents as to what you need to do. Any questions? Yes. Oh, wait a minute. There we go. Chris?
Mr. Microphone.
Yeah. In the example you showed with the cracking coming out of the oil hole that was chamfered, and this may seem like a stupid question, how about chamfering them horizontally versus vertically? You'll have a wider oil path and alleviate the flexing. Or am I wrong with that?
Are you referring to the picture that Randy had with the Magnaflux with the green cracking?
No, the other one where the oil hole was chamfered and the cracks were coming out of it.
Yeah.
That one, I actually tracked that little tool mark on that one,
yeah.
on that picture.
Oh, okay.
Yes. Yeah. No, it was tool mark.
Okay.
Yeah.
All right, questions?
All right.
Hang on.
Yeah, if we do that, if you don't mind, I'm sorry.
Going back to that oil hole where you showed it where it was like flat ground into it.
Yeah, it's teardrop.
The teardrop shape
Yes.
in there. What would you say is a better thing? Because half the time you buy these aftermarket cranks, they do that right at the manufacturing process.
Understand. And at the end of the day, once it's there, you can't change it.
Change it, right. How about the old school way where you just went in there with a little cone there and just broke the sharp edges?
Getting rid of sharp edges is crack propagation usually starts with a couple things. If you create a stress riser being a sharp point, that creates a stress point, which at that point is where the flex is, and the crack will propagate out of that. So decreasing that or adding a radius, decreasing that sharp edge is very valuable. It doesn't, you can't change the oil flow
Right.
to the bearing. That, once it's there, it's there.
But it's
you
just
know.
for the stress, yeah.
Yes.
Okay.
That is correct. But getting rid of the stress riser is key. Yes.
Okay.
Let me build on what he just said. Breaking that edge is important, but it's sort of like being a headquarters. You can get in there and really screw things up, right? And it's not intentional. You just got to be cognitive that this gig has changed. The viscosity of oil, the things we used to do, listen, 50 weight oil was pretty common in racing. Now we're talking about 0 weight. So it flows different, right? And you just got to be cognitive of what you're getting into there. So that's why I made the comment, pull it back, talk to the manufacturer, listen to him a little bit, because you know, he said there got tears in his eyes from some of the stuff he gets back. And I'm not trying to be mean-spirited, I'm just telling you, cause and effect, all right?
Dan,
Yes.
got a question. On measuring oil film pressure, how is that exactly, how you do that?
Carefully.
So it's actually, to create that is actually a data, a mathematical formula of flow, pressure, space. It's not an actual where you're taking a thermocouple or a transducer and measuring that. Is done data based. So if you calculate in what oil viscosity, a lot of stack ups. I mean, to create FEAs or oil film, it's only as good as the data you put in. You know, we create a system because we designed for OEM and to figure out what is that oil film is based on and what requirements of oil they need, or we will dictate them and say, look, you need changes to get this oil film, but it's a calculated number.
Okay.
Now, the calculated number, when you live test, and some of the examples I gave, there was a calculated number and there was live tests, and as you could see, they back each other up. So the data input, but if you just looked at the parts, you have to know what that is by either having the numbers or just physically knowing what the parts are and how this progression works.
Okay.
Anybody else got a question? There you go.
Hey, at the end there, you showed the crank snout, and I was just wondering if you had a bigger crank snout, would that help with flex of the crankshaft? Like some small block Chevys build it with a big block Chevy snout on it. Does that extra beef on the front help with torsional flex?
Yeah, because it's unsupported, so the larger diameter will help. Kind of like when I was showing the rear bearing, when stuff starts to move, and as Randy had the out of balance, and when it starts to move, having something more rigid, you know, and to go a step further, back to kind of what Randy said, with even the oil holes in lightning on the rod, the data, the force coming in there, anytime you can change the mass, you're changing the frequency, but you're also adding rigidity. I'm a big fan of bigger snouts, reducing snouts, and trying to get everything as compact, because leverage is your enemy, and size.
Okay.
Yeah, absolutely.
Appreciate that.
And to go with that, also it gives you more surface contact for press, so you reduce the chance of having movement, which again causes frictional temperature into the crankshaft, and once that starts happening, it's a snowball effect. Again, I'm not a dampener expert, but past experience has proven that.
I have a motor that we purchased. Through disassembly, we learned that the crankshaft, the rod journals were turned down.
I'm really having a hard time with this.
The rod journals were turned down to a Honda journal, inch 880, to reduce or change the stroke of the crank. But they increased the fillet radiuses quite a bit. So even though we were running the narrow bearing, I noticed after disassembly there was witness marks on that radius of the bearing. So looking at the bearing, I can see that they massaged the bearing to increase it for clearance, but they didn't do it enough. My question is, what's proper, 45 degrees, 30 degrees, and what would be the right way to massage the bearing to clear the radius, the fillet
To
radius?
chamfer the bearing? The answer is yes. There's countless ways. Our bearings, when they start doing that, you'll see a lot of them that has a suffix with an N, and it's just a narrowed bearing.
It was an end bearing.
Okay. All we did was narrowed it. There's other applications. What I was showing up here, the animation of hitting the radius, that particular was a nitro crank that we're working on to try to increase radius. That is what we're working on right now. There is going to be a chamfer change. What I've seen in the field is the chamfer maybe a 30 degrees. They're changing it to a 45. And it really isn't work. Manufacturing, I have a specification of steel I need before the chamfer, so that dictates the angle that I can put based off what we call the B wall, the thickness of the bearing. I have to have X amount of steel before I can start my cut. In the aftermarket, I've seen them cut all ways in there, but I can't manufacture it that way because of it getting too thin here. But can it be done afterwards? I've seen it. And
what's the proper way to massage the bearing for clearance?
So typically, what I've seen both ways. A fixture externally is key. In my years of engine building and stuff like that, I've made mandrels with a hose clamp, and I've tightened it up and cut them, and it worked. There's no yes or no on that. It's just protecting, not distorting the bearing, and using some finesse with it. I mean, it's kind of a vague answer, but I can't speak from the manufacturer side. I can speak from personal side and what I've seen generally in the field. So.
I just heard of guys take miles
Yeah.
You just see things flaking off the bearing.
Yeah, agree, and I do agree with that. Yeah.
All right, what's your question?
Okay, looking way back in your presentation where you were looking at the oil feed into the main bearing, historically we've all fed main bearings kind of top center because of, all of the blocks were made that way, and we just do that. The hole in the bearing goes in the top center of the block. Given the fact that that's the feed side and the crank is rotating, have you done any modeling or considered anywhere we do something to move the feed hole in the main further around in the clock so that we're taking more advantage of that low pressure area in the top of the bearing as it's rotating around?
And that's a great question about moving the oil hole in there, and some blocks have multiples. Some of the people are drilling holes, putting tangent slots in the block to double feed and doing that. And the simple, complex answer to that is as an OEM, which I don't control, we can tell them, but typically speaking, as the one picture showed, the force is showing that it's going down. Right, so in the mindset, if the force is going down, that is the largest area to add oil to fill in that volume, because the crank would be down, and simply put, then you'd light the ignition and it goes crazy. So the reality is, the pictures show you add power. Now all of a sudden that may not be. So anytime you change what was designed, there's a learning curve to go with that, and it's not a straight answer. So, and I have people run the same application with particular big block Chevy nitrous motors or something like that, and I can go shop to shop, and some guys are adding extra oil because it worked, some guys didn't, some are doing it because that's what they always did, and they may have been running a centered bearing, and they're just trying to flood oil. They've had situations, and maybe because of the crank design, and the fix was add more oil, and we just keep monkey see, monkey do doing that. Not saying it's wrong, just it's the way it is.
Well, just intuitively, it looks like we've got an area there where there's no oil being introduced, and we may have something of a negative or a more negative pressure in that portion of that oil groove, where we could take advantage of time and just flood that area on the way in and get the most opportunity we can on getting feed oil into it before it turns into a pump as it rotates.
Yeah, Inducing oil in the right time is key. That's where the oil hole phasing, as I allude to, because if you change the phasing on to the rod, you can induce more air. We'll go back in time with cross-drill cranks and 360-degree bearings. You know, that can get a point where you're actually bleeding backwards. And again, you know, I've had people here, it's like, well, I'm going to plug up one hole and get rid of the cross-drill crank. I'm like, no, you can't, because now your phasing's way off and you're feeding at that pressure side. But the problem is you're feeding at the pressure side, so a cross-drill crank, when you add power, if you're feeding at peak oil film pressure and the hole is there, you're back feeding it and it's going backwards, so now you've lost oil pressure to the main, which then ends up losing it to the rod. So it is very, if you change one thing, you may have changed 30 other, you know, pros or cons to that.
And the problem is that you do what you think, and I understand the motivation to do that, but without a controlled environment to modify what you did, a lot of times we did this and we fire it up and go race. That's Russian roulette, you know. So
yeah.
It's an unusual question, and there's not a simple answer. But sometimes Murphy's Law will grab you, and sometimes you do stuff that you accidentally made right. You know, so.
Yeah. Now,
okay, there you go.
And to go a little bit in more detail, you know, if you're building the same engine over and over and get the same, like in my case doing NASCAR, we had spec engines that we built, and Daytona used this spec, Texas used this, Martinsville used that spec. We had different specs, and I would know, and then as the reliability engineer, I would keep the data on there and electronic files, et cetera, et cetera. But I can get repeat data. But to go off and say I'm going to change this based off the situation. I mean, but these are specs that everything has been. Jimmy's familiar with what I'm talking about because of his NASCAR background. You know, if you build consistently as they did, you get repeatable results. If you make a change, you can see what's happening because you have mass quantities of the same spec engine. If you're going to go and say, oh, I'm going to fix this one-off engine and do that, you know, you feel lucky. You know, that's kind of.
All right. Any other questions? We start charging in 5 minutes.
Oh, no. Because I actually got two. So,
actually, he's the money man, so he will pay you.
Oh, so I need to start with him first. So my first question then, and we'll do it towards you. With some of the factory crankshafts, when I spin them up on the balancer, I actually see a weight difference from the front to the rear for out of balance. And typically it seems to be maybe, let's call it, close to 1/4 to a 1/2 ounce inch from the front to the rear being heavier in the rear.
I mean, every crank you put up, you see that?
With some of the factory LSs, I'll see it. And it does vary just a slight amount, but it constantly tends to be a little bit heavier in the rear than it is in the front. Is there any input with that one?
Well, and again, I'm going to try and answer this because if I see in a profile of different application cranks with the same trend line, then I'd have to go back and look at the calibration on the machine.
Okay.
It sounds like, superficially, that your inputs, listen, it's a mechanical event. So all of a sudden, every time this guy's heavier than that time, there's something going on. And it's typically within the tune of the machine. All machines have to be tuned. Calibration is the way you would talk about it. I'm not sure that's 100% the right answer you're looking for, but whenever I say trend line, then I'm thinking the measurement instrument is steering my data as opposed to reporting my data. Okay. There's a difference there. What type of machine is it? Jared?
We actually have a Sun machine with a TNS system on it.
Yeah, that's right. Listen, I'm not going to hold that against you. You know, it's all right.
He'll talk about you later, though. Don't worry about it.
I can't speak to the way you're describing and the way I'm trying to analyze it. I think it sounds like calibration.
Okay.
Okay. So I can help you with that.
Okay.
If I'm wrong, but on that LS crank, some of them are balanced without the reluctor.
Yeah, incredibly dumb.
The machine, and then they put the reluctor on.
Yeah, and they screwed it up.
It's the same brand crank and same manufacturer. That may be what he's seeing. Is the crank's balanced without the reluctance part?
Yeah, if it comes from, well, yeah, exactly. Okay, that's a good point. Because the reluctor ring evolution and the cranks are being misapplied. In other words, the OE may do a primary balance without it and then add later. In fact, I remember MAHLE doing that a while back, and I fussed at them about it, and they have since corrected it. Because what they did is they tried to do a formulation comp, and I said, it doesn't work that way. You know, you got to put it on, it has to be located and stable, and then you get a true value of unbalanced force. Okay, so good point.
And the reason I mentioned that is because I had it happen with my crank supplier at Yates.
Okay.
Where they had a balancer that was done for the weight without the reluctor and with the reluctor, and they sent me cranks that were balanced for the reluctor that we didn't run.
Oh.
Did Carson?
All 50 grams on the rear.
Did Carson do that?
Huh?
Was that Carson? We'll talk about that later.
I'm not naming them.
You start seeing a red dot show up on you.
He's not here. We know the same guy.
The first one I caught was on the dyno. I said, wow, my feet are tingling.
I'm sorry.
All right, go ahead. And so the second one, with seeing the different shaft diameters and the different RPMs that we're actually turning with it, is there any sort of journal surface feet per minute that you're actually looking for as far as developing a dynamic wedge for the oil?
No. We don't. There's a lot of talk about surface speed and reducing pin and surface speed like that. We don't view that. We don't analyze surface speed because at the end of the day is our job to figure out how to supply the right amount of oil to that journal size. Now, in calculations, because it come up to speed and what that engine is operating at, yes, there is a slight variable in there, but to sit there and say, if I change this to speed, and I hear that a lot, and I really have never found, everything I've found that says, well, the speed affected the bearings or so forth like that, when you really break it down, it wasn't the speed. There was other anomalies going on where it was improperly clearanced. The crankshaft was, there's other things, and surface speed used to be, in my opinion, a bigger topic, and to be able to do it now, I can pretty well look at parts and quench that idea because it's not with the overlays and stuff going on now. It's surface speed. I will add surface speed in cutting stuff down, Honda and so forth like that. I'm doing some work on the performance on the Godzilla engine, and they were looking at what Ben Strader's speaking on that, and that's actually the individual at EFI University, and we had a lot of concept talk on that, of where to go for a aftermarket crank and what to do, Honda, whatever. As you saw in the animations and the FEAs, where's the flex? The flex is from the rod here. So the smaller the diameter, the more flex it will allow, which puts more minutes of taper in the mains, which creates more problems. So, as they were saying, I want to add more power, but I want to go a small journal. It's like, it's opposite ends of where it needs to go. It needs to get, you need that offset to be closer, and if you want the right stroke, the only way you can do that is by making that rod journal larger, which increases the strength to decrease the pivot of it, or the flex of it.
Awesome.
Does that make sense?
Thank you guys for your time.
Sure, no problem. Thank you.
You answered what I was going to comment on. Point of diminishing return for the bearing size. The bearing speed is important, but when you diminish your cross-sectional area with stroke and all, there's a diminishing return.
You're correct.
At the point you stop it.
Right. Yes.
When it wears out.
Yep.
Rules makers come in and say, don't go no smaller.
Yeah.
Our deal is to decide how to make it make power and live. There's the common thread, right? Unfortunately, sometimes those are two different paths. Right? The horsepower guys, they know how to, I didn't even use this during the presentation. Warren Johnson said you can't tune it up if you blow it up. Well, We seem to have a propensity in this industry to think blow-ups are cool. Wrong answer. Wrong answer. How about anybody else?
Curious about that thrust bearing you talked about.
Yeah.
Ramp. Any particular angle for that ramp?
It's not. I can't tell you the angle. I can tell you the dimensions of the hole and the pad, and then basically how much ramp. The spec on that off memory is 2.5 to 4 thousandths of from flat to taper is a spec. I don't know what the angle that is. It calls out how much negative to zero angle it is in that space. It obviously you can calculate it out, but to sum it up, zero being the pad, it's roughly around 3 thousandths. And Jimmy was involved with on their deal firsthand of measuring those.
Actually started with the FR9,
Yep.
it uses half a thrust.
Yes.
And it was pressure oiled, it had extra grooves in it. I mean, we actually drilled through the bearing, put pressure there, and it didn't fix it.
Yep.
But wound up going to the CNC and putting the ramp and pad on.
Right.
Doing away with the pressure oil and all, and it pretty
Yep.
well fixed.
Yeah.
Got a well to where it needed.
That surface finish on the front.
Surface finish was surface finish.
If it has
Yep.
any grind marks in the surface finish, you gotta get that off.
Yeah. Yeah.
Use your profilometer for your cylinder.
Yep.
Make sure that surface finish is slick.
Yeah. Jimmy and myself, and collectively, we've had a lot of stuff. We work. I was at Roush Yates, he was at Robert Yates, but we worked very closely together. And then when I came here, we worked on some of the LS thrust pads, and a lot of it was surface finish up the aftermarket, because when you're grinding, and it was the side of the wheel was addressed, and it was getting this fine, so I was checking RA finish on the side of it, and it was basically this rodent. In designing of the F49, the current NASCAR Ford engine, it was a thrust insert, and we were having problems where on initial startup, they were failing thrust. Like we would start them up going to chassis dyno, and it'd be a thrust failure. Like what the heck, you know? So you'd go underneath there and you had to check implant and all that stuff. But we made the ramp and pad on we ordered sheets of what we call, basically it was steel and substrate is what it was. And we water jetted out and machined the ramp and pad exactly what I was showing on every FR9, and it eliminated. But it's, like I said, it's a 93% increase of load, because in two flat surfaces, you just can't get oil. So, the combination of ramping oil into it is the same effect as the journal is of pulling it in, right? And typically, if you look at a thrust failure, the thrust failure starts at the furthest point away from where the oil feed's going, where it's getting oil. And it goes back to the melting out the components, all right? Substrates, copper, tin, lead, all right? So it's starting to sweat out that. Typically when you see a thrust failure, you will see it almost look like solder popping out, little solder blobs that are smeared over. That's the lead tin sweating out of the substrate from frictional temperature. But yeah, it's a drastic improvement. It's not new. It's just we're just adding it on the small block, big block Chevy. It's never been on there, so we're adding those features to put more margin in the parts. Why not? Right?
All right. Do we have any other questions? All right. When you're on the way out the door, just pass the plate around.
Again, thank you very much, everybody.